Summer of 1925. Pennsylvania coal country. The engineering consensus from visiting European hydraulic specialists was absolute. Moving overburden layers 200 feet deep was mechanically impossible using American cable technology. Through the dust and diesel smoke of strip mining operations, European trained engineers observed primitive American drag lines attempting excavation work that defied everything. Continental engineering science said was achievable. No precision hydraulics, no variable fluid power systems, no computerized controls, just massive steel cables and walking mechanisms that seemed destined for catastrophic failure. In German factories, hydraulic excavators represented the pinnacle of mining technology. Infinite variable power, mathematical precision, theoretical perfection that retired American steam shovels could never match. The Europeans were operating with engineering philosophy the Americans had never seriously studied. Advanced hydraulic cylinders, sophisticated pump systems, scientific pressure calculations, excavation capabilities that reduced operating costs from $12 to $3 per ton. 8,000 miles from European laboratories, the most decisive excavation revolution in mining history was beginning to reveal itself, not in hydraulic sophistication, not in theoretical engineering, but in the systematic durability that connected every American cable strand in ways European precision manufacturing never imagined lasting. The Pennsylvania coal fields of 1925 stretched across rolling hills like a battlefield where steam and ambition had fought geology to a bloody stalemate. Oscar Martinson stood at the edge of the Keystone Mining Company's newest operation, watching their latest steam shovel strain against overburden that mocked every engineering calculation. 230 feet of rock, clay, and glacial debris separated the mining company from coal seams worth $23 per ton. The steam shovel, pride of American excavation technology for 3 decades, reached exactly 62 feet on its best day. The numbers told a story of industrial desperation. Keystone's extraction costs had climbed from $3 per ton to $12 per ton as shallow coal deposits played out across Pennsylvania. Mine operators hemorrhaged money, while European engineering journals published reports declaring deep overburden mining mechanically impossible with existing American technology. Heinrich Bauer's recent paper in the International Mining Quarterly had been particularly damning. Hydraulic excavators in German coal operations achieved consistent 60-foot reach with mathematical precision, but American conditions, freeze-thaw cycles, rocky overburden, unpredictable ground conditions, destroyed European hydraulic systems within months. Martinson crushed the technical report in his weathered hands, locomotive grease still embedded under, fingernails that had rebuilt steam engines across the Midwest for 15 years. Steam shovels managed 400 tons per hour maximum, but profitable deep mining required 2,000 tons per hour minimum. The arithmetic was brutal and unforgiving. European hydraulic prototypes maxed out at 60-foot reach before catastrophic seal failures in American mining conditions. German Krupp engineers had visited Pennsylvania mines the previous spring, declaring the overburden challenge beyond mechanical solution with current technology. But Martinson saw mining like railroad construction: build simple, build strong, build to last decades rather than quarters. Walking across the Keystone site toward his workshop, he calculated loads, stresses, and mechanical advantages with intuition earned from 20 years of locomotive repair. Steel cables used in railroad construction withstood enormous dynamic loads for decades. Walking mechanisms adapted from railroad turntables distributed massive weights across soft ground. The solution wasn't hydraulic sophistication, it was mechanical simplicity scaled to unprecedented proportions. The first prototype test that summer nearly ended everything. Monahan Machine Company's experimental walking drag line, Model 1W, featured 5-inch steel cables with 40-strand construction rated for 200,000 pounds tensile strength. The walking mechanism borrowed cast iron shoe design from Pennsylvania Railroad turntables, distributing 8,000 tons across 120 square feet of ground contact. Martinson had personally supervised every cable splice, every walking cam, every boom connection. On July 15th, the cable snapped. The 15-ton bucket crashed into the test pit with a sound like artillery fire, injuring 2 workers and destroying 3 months of careful engineering work. Martinson stared at the twisted steel cable ends, each strand precisely engineered to support 4,800 pounds, now splayed like broken piano wire. The failure analysis revealed inadequate cable termination. The splice connecting cable to bucket had pulled apart under dynamic loading conditions no railroad application had ever demanded. Competitor Bucyrus Equipment announced successful hydraulic trials in German coal mines that same week. Their press release trumpeted precision European engineering, achieving consistent 60-foot reach with mathematical reliability. American mining journals echoed European skepticism with headlines like Cable Technology, Medieval Solution to Modern Problems, and Hydraulic Superiority, Why Steel Rope Cannot Compete with Fluid Power. The financial pressure intensified through late summer. Monaghan had burned through $200,000 in development costs, equivalent to $3 million in current purchasing power, with Christmas bankruptcy looming if the walking drag line concept failed completely. European manufacturers flooded. American mining publications with advertisements promising safe, reliable hydraulic excavation that eliminated dangerous cable technology. Big Jim Morrison, mine superintendent at Pennsylvania Coal and Iron Company, visited Martinson's workshop in September with characteristic bluntness. "Oscar, I need to move overburden or I need to find new work. Your machine dropped its bucket and nearly killed my men. Krupp's hydraulic unit worked 31 days out of 84, but nobody died." Morrison's weathered face showed the strain of defending equipment choices to cost-conscious executives while ensuring worker safety in increasingly challenging conditions. "Show me why steel cables will work when German engineering can't." Martinson spent October redesigning cable terminations with locomotive-grade splicing techniques. Each 5-inch cable now featured 50-strand construction, with individual strands tested to 4,800 pounds. The walking mechanism received reinforced cam wheels capable of moving 10,000-ton loads across unstable ground. Most critically, he adopted field repairable design philosophy, every component accessible to blacksmiths and welders, working with basic tools in mine workshops. The improved Model 3W began testing in November, under conditions that had destroyed the prototype. Martinson operated the machine personally, feeling cable tension through control levers, listening to walking mechanism rhythm, watching boom deflection under maximum load. Each successful cycle built confidence, but European hydraulic advocates continued publishing technical papers proving cable limitations. Dr. Heinrich Bauer's latest report calculated cable fatigue failure after 100,000 cycles, concluding that steel rope technology represents fundamental mechanical limitation that hydraulic systems transcend through infinite operational flexibility. December snow covered Pennsylvania mining operations as Martinson prepared for the demonstration that would determine Monahan Machine Company's survival. The Model 3W faced the ultimate test, continuous operation in the Keystone Mine's deepest overburden section, moving material no American machine had successfully excavated. European competitors waited for cable failure, hydraulic system manufacturers prepared victory celebrations, and mine operators calculated backup plans for when the walking drag line inevitably joined steam shovels in technological obsolescence. Standing beside his creation on December 1st, Martinson felt the weight of American industrial reputation balanced on steel cables and walking shoes. The machine that would either validate decades of locomotive engineering experience or confirm European hydraulic superiority sat silent in falling snow, waiting to prove whether mechanical simplicity could triumph over theoretical sophistication in the unforgiving arithmetic of deep mining operations. The breakthrough came at 3:17 on the morning of December 3rd, when Martinson discovered that locomotive-grade steel cables possessed tensile strength characteristics no European hydraulic engineer had bothered to calculate. Working by lantern light in the Monian workshop, he tested individual cable strands under dynamic loading conditions that simulated 20 years of mining operations. Each strand of the 50-strand construction supported 4,800 pounds before failure, but the cable system's true innovation lay in load distribution. Dynamic forces spread across multiple strands prevented catastrophic single-point failures that plagued hydraulic cylinders. The mathematics were elegant in their simplicity. 5-inch diameter cables with 240,000 pounds per square inch tensile strength could lift loads that required hydraulic systems operating at pressures beyond current seal technology. More importantly, steel cables maintained consistent performance in Pennsylvania's freeze-thaw cycles that destroyed hydraulic seals within months. Martinson's walking mechanism adapted railroad turntable technology to distribute 8,000 tons across cast iron shoes with ground pressure of only 12 pounds per square inch, less than a horse's hoofprint, despite the machine's massive weight. Heinrich Bauer arrived at the Keystone mine site on December 10th with a delegation of German Krupp engineers carrying leather portfolios filled with hydraulic performance calculations and mathematical proofs of cable technology limitations. His condescending assessment echoed through the Pennsylvania mining community. Herr Martinson, your steel rope represents medieval engineering. Cables fatigue after 100,000 cycles through predictable metallurgical failure. Our hydraulic systems offer infinite operational cycles through proper fluid dynamics. Bauer's technical presentation at the Harrisburg Mining Association featured precise diagrams showing hydraulic cylinder advantages over primitive cable systems. Variable fluid pressure provided mathematical control over excavation forces. Electric pumps eliminated the mechanical limitations that constrained cable-operated machines. Most convincingly, German hydraulic excavators achieved consistent performance measurements that cable systems could never match through scientific precision. The Model 3W began continuous operation on December 15th, moving overburden in Pennsylvania's harshest winter conditions. Martinson operated the machine 18 hours daily, systematically proving cable system reliability through methodical excavation cycles. The walking mechanism advanced 20 feet per hour across frozen ground that immobilized tracked equipment, while the boom reached depths of 300 feet, 5 times the maximum European hydraulic extension. American mining journals initially echoed European skepticism, with headlines questioning cable technology's fundamental viability. The Mining Engineering Quarterly published Bauer's mathematical analysis, proving that steel rope systems face insurmountable fatigue limitations that hydraulic technology eliminates through scientific pressure control. Technical papers from British Steam Shovel Consortium reinforced the European position, arguing that American cable experiments represented colonial attempts to replicate sophisticated continental engineering through crude mechanical substitution. But the operational numbers told a different story. After 30 consecutive days of continuous operation, the Model 3W had moved 450,000 cubic yards of overburden without mechanical failure. Cable system maintenance required only blacksmith tools and welding equipment available at any mining operation. More significantly, the bucket and boom remained repairable on site by workers with basic mechanical skills, while hydraulic competitors required factory technicians for seal replacement and pressure system diagnosis. Tommy Kowalski, head dragline operator at the Illinois Strip Mine, visited Pennsylvania in January to evaluate the walking drag line for Midwest mining operations. His assessment cut through technical debates with practical observation. This machine works like a steam locomotive, simple, strong, and fixable by anybody with a wrench. German hydraulic unit worked 31 days out of 84, then needed factory repair for seal failure. American dragline worked every day except Christmas. The proof of concept culminated on February 28th, when the Model 3W completed 84 consecutive days of operation in the Keystone Mine's deepest overburden section. Final statistics validated Martinson's mechanical philosophy. 18,000 cubic yards per day, 300-foot maximum reach, and operating costs of $1.80 per ton, half the expense of steam shovel operations, and 60% below European hydraulic system costs. Cable system advantages became undeniable through extended operation. Steel ropes demonstrated self-maintaining characteristics as individual strand failures distributed loads across remaining strands without catastrophic system breakdown. The walking mechanism proved superior to tracked excavators on soft ground, spreading massive weights without ground penetration that immobilized conventional equipment. Most importantly, field repairs used standard mining tools rather than specialized hydraulic components requiring factory replacement. Mine foreman Big Jim Morrison submitted his official equipment evaluation to Pennsylvania Coal and Iron Company executives in March. Machine worked every day except Christmas. German hydraulic unit worked 31 days out of 84 before requiring factory service for seal replacement. Cable system maintenance accomplished by mine mechanics using blacksmith forge and welding equipment. Recommend immediate procurement of 3 additional walking drag lines for expanded overburden operations. European manufacturers responded with intensified propaganda campaigns emphasizing hydraulic system sophistication over American mechanical simplicity. Technical committees published papers arguing that cable technology represented temporary American adaptation rather than permanent engineering solution. Krupp Industries announced improved hydraulic seals designed specifically for American mining conditions, promising reliability matching German performance standards. But Martinson's vindication spread through American mining operations as operators compared actual performance against theoretical projections. The walking drag line that European engineers declared mechanically impossible had moved over 1 million cubic yards of overburden while competing hydraulic systems accumulated maintenance hours exceeding operational time. Steel cables that should have failed after 100,000 cycles showed no fatigue damage after 500,000 loading cycles. Standing beside the Model 3W in March snow, Martinson watched his creation continue excavating Pennsylvania overburdened with mechanical precision that validated decades of locomotive engineering experience. The machine Europeans called primitive had proven that American engineering strength lay not in theoretical sophistication, but in building equipment designed to work for decades rather than impress engineers for quarters. Cable technology was about to transform American mining operations in ways that hydraulic precision could never match through the simple reliability of steel rope and American mechanical intuition. Orders flooded Monaghan Machine Company through the spring of 1926 as mine operators witnessed the Model 3W's unprecedented performance statistics. 47 walking drag lines sold by December, with production schedules extending into 1928. Each machine featured Martinson's perfected cable system, 5-inch steel ropes with 50-strand construction, walking mechanisms distributing 10,000 tons across elliptical cast iron shoes, and boom assemblies reaching 400 feet with 85 cubic yard buckets that dwarfed European hydraulic equipment. The Illinois strip mine reported staggering productivity numbers after installing their first Monahan 5W dragline. Tommy Kowalski operated the machine through brutal Midwest weather conditions, moving 2.1 million cubic yards in the first operational year, productivity figures that European hydraulic manufacturers dismissed as American propaganda until independent mining engineers confirmed the statistics through direct measurement. The walking dragline's ground pressure of 12 pounds per square inch allowed operation across marshland that immobilized tracked excavators, while cable systems maintained consistent performance through temperature variations that destroyed hydraulic seals. Martinson's walking innovation revolutionized dragline mobility through his perfected cam wheel mechanism. The elliptical shoe motion enabled 10,000-ton machines to advance 20 feet per hour across unstable ground by lifting and placing massive cast iron shoes in precisely coordinated sequence. Unlike tracked vehicles that compacted soil under continuous pressure, walking draglines distributed weight dynamically, preventing ground penetration that trapped conventional excavators in soft conditions. Mining operations across the Midwest discovered that walking draglines could traverse terrain impossible for wheeled or tracked equipment while maintaining excavation capabilities. American mining productivity exploded through 1927 as dragline technology enabled previously impossible excavation projects. Coal production increased 340% in 3 years as operators accessed deep, overburdened deposits that steam shovels couldn't reach. The versatility advantage proved equally significant. Identical machines stripped coal seams, constructed flood control levees, and dredged harbor channels with operational flexibility that hydraulic excavators couldn't match through specialized design limitations. The Mississippi River flood crisis of 1927 provided dramatic proof of American dragline superiority over European hydraulic alternatives. When spring floods devastated Louisiana parishes, emergency response teams deployed both American walking draglines and European hydraulic excavators for massive silt removal operations. 3 Monahan draglines moved 12 million cubic yards of flood debris in 8 months, while 6 competing hydraulic machines managed only 3.2 million cubic yards before succumbing to pump failures, seal breakdowns, and electrical system damage from flood conditions. Louisiana State Engineer Robert Thibodeau documented the performance differential in his official flood recovery report. The American cables sang in the wind during continuous operation, but they never broke under maximum loading conditions. European hydraulic pumps screamed under pressure, then died from seal failure or electrical damage. Walking draglines operated through conditions that destroyed sophisticated hydraulic systems within weeks. The Flood Recovery Project established walking draglines as the preferred equipment for emergency excavation operations across the American South. European manufacturers responded with increasingly sophisticated hydraulic designs featuring improved seals, variable pressure systems, and precision controls that promised reliability matching American cable performance. Krupp Industries announced their Mark IV hydraulic excavator with revolutionary fluid dynamics that eliminated previous seal failure problems. British Steam Shovel Consortium introduced electrically controlled hydraulic systems that provided mathematical precision impossible with mechanical cable operations. Technical publications emphasized hydraulic sophistication over primitive American rope technology, but operational reality contradicted European marketing claims. Mine operators who tested both systems discovered that hydraulic excavators required factory-trained technicians for repairs, while dragline maintenance used standard mining tools available at every operation. Hydraulic systems demanded clean fluid conditions impossible in mining environments, while cable systems operated reliably despite contamination that destroyed precision hydraulic components. Most significantly, hydraulic excavator average operating life measured 12 to 15 years, while draglines built in 1926 continued productive operation through the 1960s. The walking dragline's mechanical advantages became legendary through dramatic rescue operations that hydraulic excavators couldn't accomplish. During the 1928 Ohio River ice jam crisis, a Monian dragline walked across frozen marsh conditions to reach stranded communities, breaking ice barriers while maintaining precise excavation control. European hydraulic units remained immobilized on solid ground, unable to traverse unstable conditions that walking mechanisms handled routinely. Tommy Kowalski's operational expertise elevated dragline performance beyond engineering specifications through intuitive machine control that mystified college-trained hydraulic operators. His ability to place 85 cubic yard buckets with surgical precision while maintaining production schedules seemed impossible to outside observers, but reflected the mechanical sympathy possible with direct cable control systems. Hydraulic excavators required mathematical calculations for pressure adjustments, while experienced dragline operators felt load conditions through cable tension transmitted directly to control levers. Production statistics by 1928 validated American mechanical philosophy over European hydraulic sophistication. Walking draglines averaged 22,000 cubic yards daily across multiple mining operations, while competing hydraulic excavators managed 14,000 cubic yards before requiring maintenance intervals that European manufacturers preferred not to publicize. Cable system reliability enabled continuous operation for months without mechanical failure, while hydraulic systems required scheduled downtime for seal replacement, fluid changes, and pressure system recalibration. Monaghan Machine Company expanded production facilities through 1928 to meet international demand from mining operations that witnessed American dragline performance statistics. 89 walking draglines sold in 1927, with orders extending through 1930, despite European manufacturer price cutting designed to preserve hydraulic market share. Each machine incorporated Martinson's field-tested improvements, reinforced walking shoes, upgraded cable tensioning systems, and boom assemblies designed for decades of continuous mining operation. The walking dragline revolution peaked in 1928 when American mining productivity surpassed European levels for the first time since industrial mechanization began. Cable technology enabled excavation projects that hydraulic systems couldn't attempt, while walking mechanisms provided mobility advantages that transformed mining operations across difficult terrain. Martinson's simple mechanical design had proven that American engineering strength lay not in theoretical complexity, but in building equipment that worked reliably for decades, under the harshest operational conditions industrial civilization could devise. The stock market collapse of October 29, 1929, devastated American mining operations with merciless efficiency. Orders for walking draglines evaporated overnight as coal companies faced bankruptcy and construction projects disappeared from corporate budgets. Monaghan Machine Company's order book, thick with contracts worth $14.7 million in September, contained cancellations totaling $12.3 million by Christmas. Martinson watched 3 years of vindicated engineering excellence crumble under financial forces that rendered superior technology irrelevant to survival. The catastrophic failure at Harlan County Mining Company on December 15th provided European hydraulic manufacturers with propaganda opportunities they exploited ruthlessly. During routine overburden stripping, Electrical controls on the company's newest Monaghan dragline short-circuited during a winter storm, causing the boom to drop suddenly and sending the 200-ton bucket crashing into the operator's cab. Tommy Sullivan, a 28-year-old dragline operator with 5 years' experience, died instantly in the twisted wreckage. Investigation teams from the Kentucky Mining Commission determined that faulty electrical wiring caused the boom failure, completely exonerating Martinson's cable system design. The steel cables had performed flawlessly under emergency conditions, maintaining tension even during the electrical malfunction that dropped the boom. But newspaper headlines screamed, "Death Machine kills again," and dangerous cable technology claims another victim, while editorial writers demanded federal regulation of primitive American mining equipment. Heinrich Bauer orchestrated a sophisticated propaganda campaign through international mining publications, emphasizing hydraulic safety advantages over dangerous cable systems. His technical papers argued that electrical control failures proved cable technology's fundamental inadequacy for modern mining operations, while hydraulic systems provided fail-safe protection through pressure relief valves and mechanical backup systems. European manufacturers flooded American mining, journals with advertisements promising German precision engineering eliminates deadly cable accidents. The coordinated European counterattack combined technical criticism with predatory pricing designed to eliminate American competition permanently. Krupp Industries offered hydraulic excavators at 60% of walking dragline cost, while British manufacturers provided financing terms that cash-strapped American mining companies couldn't refuse. German engineering teams visited major mining operations conducting safety evaluations that invariably recommended replacing dangerous cable systems with reliable European hydraulic equipment. Monaghan's market share collapsed from 67% to 23% in 18 months as mine operators canceled existing orders and selected European alternatives for new projects. The Kentucky accident investigation proved cable system innocence, but public perception had shifted decisively against American dragline technology. Insurance companies raised premiums for operations using walking draglines, while labor unions demanded safer hydraulic excavators to protect worker lives. Big Jim Morrison faced brutal pressure from Pennsylvania Coal and Iron Company executives, who demanded explanations for supporting equipment that killed operators and generated lawsuits. His operational statistics showed walking drag lines maintained superior productivity and lower maintenance costs, but corporate attorneys focused on liability exposure rather than mining efficiency. Morrison's defense of cable technology seemed increasingly futile as European hydraulic marketing emphasized safety over performance. The price war intensified through 1930 as European manufacturers sold hydraulic excavators below manufacturing cost to capture American market share. Krupp's latest models featured improved seals designed for American conditions, variable pressure systems that promised operational flexibility, and sophisticated electrical controls that eliminated mechanical complexity. Technical demonstrations showed hydraulic precision that cable systems couldn't match through mathematical control over excavation forces. Sir Reginald Whitmore coordinated British manufacturers' assault on American dragline technology through formal complaints to international mining standards committees. His carefully orchestrated campaign questioned cable safety standards, challenged American testing procedures, and promoted European hydraulic regulations as superior to primitive American mechanical designs. British Steam Shovel Consortium published technical studies proving that cable fatigue created inherent safety hazards that hydraulic systems eliminated through advanced engineering. Martinson faced personal and professional ruin as Monaghan Machine Company hemorrhaged money through canceled orders and legal expenses from the Kentucky accident lawsuit. His walking drag line sat in factory yards gathering rust while European hydraulic excavators captured contracts that represented decades of American engineering development. The cables that had moved millions of cubic yards without failure became symbols of dangerous obsolescence rather than mechanical excellence. Independent accident investigations vindicated cable technology completely, proving that electrical system failure caused the Kentucky tragedy rather than mechanical inadequacy in Martinson's design. The National Mining Safety Commission concluded that steel cable systems performed as designed during the accident sequence, maintaining structural integrity under emergency conditions that would have destroyed alternative lifting mechanisms. But technical vindication couldn't overcome public perception shaped by European propaganda and sensationalized newspaper coverage. American mining productivity declined as operations replaced reliable walking drag lines with hydraulic excavators that required specialized maintenance, factory trained operators, and frequent seal replacements. European machines averaged 45% uptime during first year operations, while replaced walking drag lines had achieved 92% availability through simple mechanical reliability. The superior technology was losing to inferior alternatives through marketing manipulation rather than engineering competition. The economic depression deepened public suspicion of American industrial innovation as unemployment soared and businesses failed across traditional manufacturing regions. European hydraulic manufacturers positioned themselves as stable, established suppliers offering proven technology, while American dragline producers appeared risky and experimental despite superior operational records. Financial survival required immediate sales rather than long-term performance validation. By December 1930, walking dragline technology faced extinction through coordinated European competition that combined propaganda, price manipulation, and regulatory pressure rather than engineering superiority. Martinson stared at twisted cable samples in his workshop. The same steel ropes that had revolutionized American mining now displayed as evidence of primitive mechanical design. The Europeans had discovered that destroying superior American technology required marketing warfare rather than technical advancement, and they were winning decisively through perception manipulation rather than performance comparison. The cables were perfect, but the world wanted imperfect machines that looked perfect through sophisticated European marketing rather than mechanical excellence proven through decades of reliable operation. The vindication came slowly through the 1930s and 40s as mining operators who retained walking draglines discovered an uncomfortable truth about European promises versus American reality. Machines built in Martinson's workshops during the boom years of 1926 continued excavating coal overburden while sophisticated hydraulic excavators accumulated in equipment graveyards across Pennsylvania, Kentucky, and Illinois. The cables that European engineers declared primitive outlasted precision hydraulic systems by decades of continuous operation. Tommy Kowalski, now supervising dragline operations across 3 Illinois mining districts, documented the performance differential with brutal honesty in his 1942 operational report. Walking drag lines installed in 1927 had moved an average of 47 million cubic yards each with minimal mechanical failures, while European hydraulic excavators averaged 12 million cubic yards before requiring complete system replacement. The steel cables sung the same steady rhythm through 15 years of continuous operation, while hydraulic pumps screamed briefly before dying from seal failures, contamination damage, and electrical system breakdowns. The Marion 6360, christened the Captain when it began operation in 1965, represented the ultimate evolution of Martinson's cable technology. Built for Central Ohio Coal Company's massive strip mining operation, The walking dragline featured a boom extending 310 feet with a 180 cubic yard bucket suspended from 8-inch steel cables rated for over 1 million pounds tensile strength. The walking mechanism distributed 15,000 tons across shoes covering 240 square feet, enabling operation across marshland that immobilized every tracked excavator ever tested. European hydraulic manufacturers watched with growing dismay as American drag lines achieved operational statistics that contradicted every theoretical limitation they had promoted for decades. The captain moved 809 million cubic yards over 26 years of continuous operation, working 3 shifts daily through Ohio's harshest weather conditions. Hydraulic excavators introduced during the same period averaged 45 to 90 million cubic yards before mechanical failure forced retirement, while cable-based machines built in the 1920s continued productive operation into the 1980s. Big Muskie, the ultimate expression of walking dragline technology, began operation in 1969 with specifications that dwarfed European hydraulic capabilities. The machine's boom extended 310 feet with a 220 cubic yard bucket, larger than a 12-room house, suspended from cables capable of lifting loads exceeding 1 million pounds. Over 22 years of operation, Big Muskie moved 608 million cubic yards of overburden, while hydraulic competitors struggled to achieve 50 million cubic yards before requiring complete replacement. The mechanical advantages that Martinson had identified in 1925 proved decisive through decades of comparative operation. Steel. Cables remained field repairable using welding equipment and blacksmith tools available at every mining operation, while hydraulic cylinders required factory replacement when seals failed or cylinders cracked under pressure. Walking mechanisms based on railroad technology lasted 40 years or more with basic maintenance, while hydraulic systems averaged 8 to 12 years before expensive overhauls became economically prohibitive. Retired dragline operator Frank Kowalski, Tommy's nephew, provided the most telling testimony about technological superiority during a 1985 mining industry conference. "We could fix anything on those old drag lines with a welder and a crane. Modern hydraulic machines need a computer and a prayer. When cables wore out, we spliced new sections and kept working. When hydraulic seals failed, we waited 3 weeks for factory parts and hoped the replacement lasted longer than the original." The economic comparison proved even more devastating to European claims about hydraulic superiority. Lifetime operating costs for cable drag lines built in the 1920s averaged 12 cents per cubic yard moved, while modern hydraulic excavators cost 48 cents per cubic yard through shorter operational lives, higher maintenance expenses, and complex replacement part requirements. Simple American engineering worked because it was designed for decades of reliable service rather than quarterly profit optimization. European hydraulic technology faced a fundamental design flaw that marketing campaigns couldn't overcome: planned obsolescence built into systems requiring frequent replacement rather than indefinite repair. Hydraulic seals degraded chemically over time, regardless of usage patterns, while steel cables maintained tensile strength through decades of continuous loading cycles. Hydraulic pumps contained precision components manufactured to tight tolerances that prevented field repair, while cable systems used mechanical principles that mining mechanics understood intuitively. The final irony emerged through modern mining statistics that vindicated Martinson's mechanical philosophy completely. Cable dragline technology moved over 3.2 billion cubic yards across all American machines between 1925 and 1991, when environmental regulations ended large-scale strip mining operations. Modern hydraulic excavators introduced since 1991 have moved 847 million cubic yards total, less than Big Muskie alone achieved during its operational lifetime. Contemporary mining operations discovered that sophisticated hydraulic systems required specialized diagnostics, computer controlled maintenance schedules, and factory trained technicians for repairs that cable drag lines accomplished with basic tools and mechanical intuition. Average hydraulic excavator retirement occurs after 15,000 to 25,000 operating hours, while walking drag lines routinely exceeded 100,000 hours before major overhauls. Planned obsolescence had replaced engineered permanence as the driving force behind excavation equipment design. The modern mining industry faces equipment costs that would have shocked 1920s operators. Today's hydraulic excavators average 50 to 80 million cubic yards moved before retirement, compared to cable drag lines that routinely exceeded 300 million cubic yards during operational lifetimes spanning multiple decades. Maintenance expenses consume 40 to 60% of operational budgets for hydraulic equipment, while cable systems required 10 to 15% for routine maintenance performed by mine mechanics. Oscar Martinson had understood what Silicon Valley entrepreneurs forgot in their pursuit of disruption and innovation. The most advanced machine is the one that's still working when everything else has failed. In 1925, he built equipment designed for the next century using mechanical principles that would outlast every technological fashion change. His walking drag lines moved mountains for decades, while sophisticated alternatives accumulated in scrapyards, proving that American engineering excellence lay not in complexity, but in the patient reliability of steel cables and walking mechanisms that worked long after European hydraulic promises had been forgotten. The cables that European engineers called primitive had outlasted hydraulic sophistication by the simple virtue of mechanical permanence over planned obsolescence.